Please title these notes Geometric Applications Notes 1, Introduction to Area. Write the little drawing that's right here. By the end of this lecture, you should be able to write an integral expression that will give you the area under the curve of a function or between two different curves. So let's start off going back to what we had at the beginning of our work with Riemann sums, which is just this idea that mathematicians had a lot of trouble figuring out the actual area under a curve from, let's say, A to B in this example, but that they could get close to the area, approximate the area under the curve, by drawing a bunch of little rectangles and then multiplying the height times the width of each rectangle to get the area, and then adding up those areas. So in this example that we have right here, the area is going to approximately equal the height times the width of this purple rectangle plus the height times the width of the blue rectangle plus the height times the width of the green rectangle, or approximately 28. So the general idea that we have is to get the area from A to B we should start at A, multiply the height and width of each rectangle to get the area. Add the areas. Stop at B. Now, the problem facing us when we use this method is that the rectangles up here don't touch the curve exactly. There's this little gap up here and here and here, making our estimate right here an underestimate of the actual area under the curve. To get the exact area, we need there to be no gaps. The question is, how do we do this? So let's write down our goal. To get the exact area, we need to draw rectangles with no gap. How can we do this? Well, unfortunately for us, if we have a curve, so let's just try a couple things here. I know that if I draw a rectangle like that, there's going to be this gap here. Not good. So I'm going to try drawing a thinner rectangle. How about that? Well, it turns out that if I zoom in and I look really closely here, there's still a gap. And even if I try doing this as thin as I possibly can, if I look really closely right there, still a gap. So, if a rectangle has any width, there's still a gap. So this caused big problems for mathematicians until they came up with the idea of, well, let's make a rectangle that's so infinitely thin that there really is no gap. It's an infinitely thin width. Like so. This was great for solving the problem, but mathematicians really choked on the idea of an infinitely thin width. It actually took quite a long time for this idea to win acceptance. Now that it has, however, it makes life a lot easier for us as long as we know a couple things about it. An infinitely thin width is called a differential. And it is written dx if the width is in the x direction, or as dy if the width is in the y direction. So an infinitely thin rectangle like that versus like that. This width here is dx because it's going side to side if we were to draw it into an actual regular rectangle. And this one, this is dy because the width, if we were going to make an actual rectangle, this width is in the y direction. Another important thing to note is an infinitely thin rectangle has a height exactly equal to the value of the function at that point. If this is our function, when x equals a and we draw our infinitely thin rectangle, height is the value of the function at a. We're going to assume this is f of x. And then width is dx because the width is going in this x direction. So to find the area from A to B of that curve that we were just working with, we're still going to do exactly the same thing. We're going to take a bunch of infinitely thin rectangles and so on. And we're going to add up the height times the width of each rectangle. Remember, this width is this infinitely thin. This little width right here times whatever this height is for each one. We're going to add up each of those, starting at our starting number over here at A and ending at our stopping number over here at B. And the thing is, if we can write an expression for the height of each of these infinitely thin rectangles in terms of the same variable that we're using for width, then we can use integration to find the area. So let's write that out. So let's say the equation of this curve is that f of x equals the square root of x plus 2, then we can say that the area is the integral from our starting number to our ending number. We know that our infinitely small width is in the x direction, so it's going to be dx. And then the height of each rectangle, whatever the value is for x, this height is f of x, or root x plus 2. This right here is called an integral expression, and in this case it's for the area under f of x between a and b. So what we're going to be asked about in the problems for this set of notes is we're going to be asked to write an expression, an integral expression to find area. So let's just write down the steps that we're going to have. So to write an integral expression for area, first you're going to be drawing a sample infinitely thin rectangle, and marking the width as dy or dx. Then we're going to write an expression for the rectangle's height using the same variable that's in the width. And then we're going to find the starting and stopping values. So let's look at some examples here. Write but do not evaluate an integral expression that gives the area of each of the following. So that just means we're going to set it up just like we were just doing, but we don't have to find a number, which is what evaluating means. So the area bounded by, that just means that there's a boundary. F of x, that's this. The x-axis, that's down here. And that's the line x equals 1 and x equals 2. So we're looking at this area right here. Now what we want to do is we want to cover this in little tiny infinitely thin rectangles, but to avoid having to draw them out over and over and over, we only have to draw one. However, we should pick how we draw that, such that if we did continue drawing them in both directions, we would always touch the same thing at the top and the same thing at the bottom. So for example, we don't want to draw them this way because we would be going from here to here for part of it, and then up here we would be touching this on one end and this on the other end. So the width down here is in the dx direction, so we're going to be doing an integral in terms of dx. We want to look at what's giving us the height of this rectangle, and the height of this rectangle is from the x-axis up to this line f of x. So the height of it is just whatever our x is. When we plug that into f of x, the number that we get. So the height is just f of x. We're starting, we want to say where's the first rectangle we would draw. That would be at 1. And the last rectangle we would draw, that would be at 2. What we can also do is we can plug in this because we know what f of x is. So we would say the integral from 1 to 2 of the square root of x plus 2 dx. And there's our answer. Sometimes though we're going to be working with multiple curves like this one right here. it's saying we want to have the area bounded by f of x, that's this one, g of x, the line x equals 2, and the line x equals 3. So there's x equals 2, there's x equals 3, and then here's f of x, and here's g of x. Again, we want to draw our sample rectangle. So if I draw them like this, then I'm going to touch the same thing at the top and bottom all the time. This width here is dx. So I'm starting, my first rectangle's at 2, my last one's at 3. So we've got the integral from 2 to 3. Width is dx. But how do we figure out the height? Well, we know that this number up here is going to be whatever g of x is, because this whole thing is g of x. And we know that g of x gives the distance from the x-axis all the way up to the top. This f of x here, this is going to give us the distance from f of x to the x-axis. So basically what's going on, this distance, that's g of x. This distance, that's f of x. And this distance right here is that we started off with g of x, and then we took away this little piece down here that we don't want. So the height that we're looking at here is g of x minus f of x. Or, since we know what g of x is, we can write this as the integral from 2 to 3. So g of x is negative x minus 2 squared plus 2.5. And then subtract whatever f of x is, x minus 3 squared plus 0.5 dx. So let's look at a similar one. This just says the area bounded by f of x and g of x. So it's not telling us to start at a particular number. It's just saying this whole thing, f of x, g of x. And we still have our same little representative rectangle. And it's still got the same dx. So we're still going to have our integral in terms of dx. And we've still got our top function, which is g of x. And then subtract our bottom function, which is f of x. But we don't know where our starting and our stopping rectangle would be, because clearly we'd start over here. And since we don't know what it is, let's just call that a. And we'd stop over here, so let's just call that b. So in later lessons we're going to figure out how to find those numbers, but for now, let's just say it's going from a to b. Just like we did up here, we can substitute. And there we go. So this pattern that we see here is the same one that we're going to see in all the other ones. If we're trying to find the area bounded by two different functions, then when we're finding the height, it's just going to be the top function subtract the bottom function. So let's see, so this one's between when x is -1 and when x is 1. And it's bounded by g of x and f of x. So we can draw our rectangle. And we see that we're starting at -1. Or first rectangle's at -1, last rectangle's going to be at x equals +1. dx is our width. And then our height is just this top one, which in this case is f of x. Subtract this bottom one, which is g of x. Plug in the equations that we have. Voila. Here are some more examples. Still that same idea though. Bounded by just means enclosed by, so we've got g of x and h of x. Here's a sample rectangle. The infinitely thin width is in the x direction, so that's dx. Got the integral. This time we can actually see the number for our starting point. It's again at -1. We can actually see the number for our ending point. That's at 2, very convenient. Our width is dx. G of x here is on top during the section that we're trying to find, so we've got -x squared. Oh, let's write it out this way first. G of x minus h of x. And when we substitute that, g of x is -x squared plus 2. H of x is -x dx. Occasionally we run into one that's a little bit more complicated. So the area bounded by f of x, this is this, g of x, and the x-axis. So that's this area right here. But one of the things that we notice is that to draw rectangles, we have to draw them so that they're touching the same thing all the time. And right here, this is going from the x-axis to g of x. But at 1, it switches and starts going from the x-axis to f of x. Well, what am I going to do about it? One thing that I can do is I can divide this up so that I have two different areas here. This one over here is just between g of x and the x-axis. This one's just between f of x and the x-axis. So I can do two little expressions. One has a rectangle over here. One has a rectangle over here. They're both dx. And just like we've done in the past, I'm just going to add up those two areas. So my first one, why don't I do it in blue over here. Starting at 0, that's my first rectangle. My last rectangle's at 1. It is a dx. And I'm doing this top one, g of x, minus the x-axis, which is the function y equals 0. So I can do g of x minus 0 or just plain old g of x. And this is just ending on that x-axis there. Then to that, I'm going to add this purple one. I'm starting at 1. Ending at 2. The width is dx. So I'm taking f of x and I'm subtracting the x-axis, which is just y equals 0. So I can do f of x minus 0 or just f of x. And then go ahead and substitute those in. G of x is the square root of x. F of x is x minus 2. Be aware of ones like this. You do need to know your quadrants. So if we're talking about the area in the fourth quadrant, that's the area down here. So it's bounded by g of x and h of x, so it's bounded by this, and if it's in the fourth quadrant, it can't go up above here. So what we're going to do is we're going to draw our little rectangles. And once again, this part is going between the x-axis and h, and then this part over here, we see our rectangles going between g of x and h of x. So once again, we're going to need to have our two different pieces. I'm going to go ahead and do this one again in blue. But both of these are dx. So for this blue one, we don't know what this is, so I'm just going to call that a. It's whatever number that is there. We'll find it in later lessons. And I'm going to say that this first one, I can see that I'm starting at 0 and ending at whatever a is. It's a dx. And I'm going to take this top one and then subtract this bottom one. So this top line is just at y equals 0, so 0 minus h of x. And then to that I'm going to add, we're clearly going from whatever a is to 2. This one's on top, that's g of x. I'm going to subtract this one on the bottom, that's h of x. And it was a dx for the width. So, plugging those in, g of x is negative x squared plus 2 minus negative x dx. The same idea is right here. We want the area bounded by f of x, that's this curve, and g of x, that's that curve. But notice how there are two different areas. Over here, g of x is on top. Over here, f of x is on top. So I'm going to mark those in two different colors. So for the blue one, our first rectangle would be at negative 2. Our last one would be at 0. It's a dx. And since g of x is on top and f of x is on the bottom, my height is going to be g of x minus f of x. For the purple one, f of x is on top, g of x is on the bottom. So we're starting at 0, we're ending at 2. I'm going to do f of x minus g of x. When I plug those in, that will give us g of x is 3x cubed minus x squared minus 10x. Subtract all of fx, make sure it's in parentheses, negative x squared plus 2. This part is negative x squared plus 2, and then we're going to subtract this whole g of x, 3x cubed minus x squared minus 10x. And that width was dx. Looks kind of icky. For now, all we're going to worry about is writing it out. This concludes Geometric Applications 1 notes.